It is recording right now.
Oh, Jared!
Jared, you DO double Snacks!
All right, so our objectives for this section. We're going to talk about different types and rates of evolution. We're going to compare different types and rates of extinction. It seems like rates of extinction, rates of evolution, seems like those things don't really go together. In fact, they're kind of opposites of each other. What is an extinction?
Like,
Dead. They can't
completely
come back.
gone.
Where a
Can't come
species
back.
disappears, it's never going to come back, it's gone forever. Right? Hopefully, a species would not go extinct. Instead, it would adapt and evolve to its environment so that it can actually survive. So these things are actually opposites, but they're actually really important to each other. When you talk about extinction, we'll talk about mass extinctions. There was a mass extinction at the end of the Mesozoic era that's actually really, really important to us. What died out at the end of the Mesozoic?
Dinosaurs.
And if the dinosaurs hadn't died out and left behind resources and niches and opportunities for mammals, mammals would not have evolved to potentially make humans, right? We'd still be tiny little furry creatures hiding under rocks trying not to get eaten by T-Rex, right? So if it wasn't for that mass extinction, we wouldn't have been able to evolve the way that we did. So extinction and evolution go hand in hand, and they are actually important to each other to a certain extent. We couldn't exist if, and maybe there'd be some smart talking dinosaur walking around right now, but it wouldn't be a mammal, it wouldn't be a human, more likely than not, if they hadn't gone extinct. So you guys have heard about that at least, or we've talked about that a little bit before. So they do go together, so we'll talk about both. We're going to start out with these types and rates of evolution. So we talked a lot about how natural selection's not really random. Mutations and drift can cause random things to occur, but if it's just natural selection, it's always pretty reasonable, obvious what's going to be selected. It's got to be something that's beneficial, it's got to be something that would help that organism, so it's pretty straightforward. But there are two different types of evolution, convergent and divergent. In convergent evolution, we're going to have evolution of similar characteristics in unrelated species. Which actually should be kind of familiar to you guys. I need an extra page here, so let me insert one. So if I had species A, species B, convergent evolution causes them to end up with some similar trait. It's called convergent because they actually come together, right? So they were different, but now they're kind of similar. As opposed to divergent would actually mean that they divide, that they separate, and are starting to look more different as opposed to becoming similar. But this convergent evolution, again, we got unrelated species. They become superficially similar. Do you guys remember talking about that? What kind of structure was superficially similar but was not indicative of relationships?
Analogous.
Analogous. Yes, that's an example. But analogous was the word I was looking for. So you need to write that into your notes because I'm sure there will be a question like that at some point. Convergent evolution leads to analogous traits. They happen to evolve that similar trait because they both needed it, but they're not related initially. They just end up looking similar. So when we talked about, in an example before, when we talked about wings, whether it was a bat wing or a bird wing, they both have wings, but they didn't get it from a common ancestor. They just converged on that trait independently because of natural selection. they both had a similar environmental problem to solve. They needed to be able to travel distances to get to all the resources that they needed, and wings were the best idea for that, the best solution for that problem. So just because they both have wings does not mean that they're related. That's actually likely to be analogous in that context. So remember, unrelated, analogous, those are convergent. So it's just a new word for the same concept we talked about before. It's convergent evolution if they end up with the same trait, although they're not related. It's divergent evolution if it's the other way around. If they become different because they're evolving in different environments, it's divergent evolution. This picture would look more like this. You got species A. One population ends up with this trait. The other population ends up with another one. So two different traits, trait 1, trait 2.
Would that be like fireflies?
Yeah, it could be fireflies that are flashing 2 times a second or 5, or the other way around. Once every 2 seconds, once every 5 seconds. That could be possible. But again, divergent is kind of the opposite of convergent because they're actually separating instead of coming together, dividing instead of coming together. So if it's not analogous, what was the other word?
Homologous.
Homologous. So this time, divergent, homologous, they are related. They end up different, but that doesn't actually mean that they're not related. It just means that they've evolved in different ways to different environments. Versus that convergent, where they're unrelated and they're analogous. This one, they're related, they're homologous. This example would be more, instead of bird wings and bat wings, we'd be talking about that bat wing versus your hand. Underlying structures are still the same, but they have completely different purposes, so they do have different traits overall. So the evolution that led to the one mammal, the bat, having wings and being able to fly, as opposed to you, a mammal, having your hands that you use to work with tools and everything else, right? That would be divergent evolution as opposed to convergent evolution, where you have wings with bats and birds that are not related to each other. So maybe be a little bit more specific here just for Jared's sake there. Although I think he's probably got the idea. And this would be the bat wing versus your hand. So one's an example of convergent because they are not related, although they end up with that similar trait. The other one is divergent because they end up with those different traits. The wing, the hand, although they are related, I don't know, you guys probably don't use these words all that much. Although there's that book series out that has this in it, right? Everybody read that?
Sure.
I've read that series, so I can't be the only one in here. But anyway, the funny part, right, you read those, it's a book, it's a movie, it's cool and everything. It's actually about evolution, surprisingly enough.
Yeah.
So if you've ever read it and actually gone all the way through it or actually watched all the movies, it is actually about evolution and an experiment with humans, and so you just have to watch the whole thing to understand it, or read the whole thing to understand
I
it.
don't
But
know.
it is technically about evolution, so when they use divergent there, that's kind of the purpose.
But they didn't go into that in the movies as much. Like,
They did in the movies. I've never seen the movies. I only read the books. So
I finally watched the movies, so nowhere near as good as the book.
they were pretty good books. I like them.
Yeah,
Might as well-
work.
So if you haven't read them, go for it. They are actually pretty good. I like them. Okay, so if you guys focus real quick, we do have a whiteboard question here. Some of us maybe already started on it, which is great. But this is basically an example that I could have thrown at you last chapter, analogous, homologous, that kind of stuff. But you're supposed to think about this the same way you did before. Are these two things related or are they not related? How would you know if they're related or not? So, are the shells of snails and turtles examples of convergent or divergent evolution? So you got to pick one or the other, write it on your whiteboard. Make sure you explain, though, too, why do you think it's this answer? Because last class, we had different answers. Some of us said divergent, some said convergent, but at the end of the day, nobody really had a good explanation. And you have to understand that I need to know why they're either related or not related. And you need to talk about structures, not about, even if you do know what group that animal belongs to or whatnot. But just saying that a bat's a mammal and a bird's a bird, more related to reptiles, doesn't really tell you why that they're not related. Why is one different than the other, though? If you were actually to talk about the hair or the live birth or the milk that mammals use to feed their offspring, those are traits that actually separate two things. So you might have to actually be specific. What do I do with your sticks? I already got them out, I guess. You grab an eraser already? Play. Alright, so I see some different answers on different whiteboards, and that's not a problem. You need to support your answer either way. So you could actually get half credit even if you have the wrong answer. If you actually support it correctly, you can, in theory, do that. So first off, Mary, what do you have to share here? You had convergent. Why did you think convergent? So you picked this one, right? So if it's convergent, that means that they have similar traits. What's the similar trait? But it also means what? Are they related or not related? How do you know that those two things are unrelated? So we don't really have support for that answer completely yet.
I
Could be reasonable. What if, I'm not saying that that's the right answer yet. I'm just saying we don't have support for that answer yet, so that kind of be necessary. Corbin, what'd you have?
Oh, jeez. I had convergent as well.
Same thing. So they had a similar trait?
My explanation is the shells and how the shell is on the snail. The snail's shell is more arching than the turtle shell. But they both use it for protection.
Okay, so now you're making it start to sound like there's two different traits, like they're different things.
Oh, did I get a flipper?
Did they inherit that from a common ancestor?
Oh, jeez, I got a flipper. Oops.
So you're making it sound like they're different traits. Although maybe you're talking about underlying structure. You're talking about like how the shell's made or what it's made from.
Like, it seems like the turtle shell a lot more harder than the snail shell.
Okay, so we're on to the next one. Jake, what'd you have?
They're examples of convergent evolution because they both have shells and they're both analogous.
How'd you know it was analogous?
Because he told us.
I didn't tell you that.
Yeah, he did.
You're assuming that they have different ancestors. How would you know that?
Because one leaves a slimy trail behind him and the other one has feet.
Turtles are kind of slimy. I don't know.
Turtles are not slimy.
They're just wet
No, they aren't.
from the water.
Anyway,
It's not in the water. There's no.
does anybody have a real reason for one or the other? Anybody want to share?
There. Oh.
What do you think, Kate?
I'd put convergent because the shells are a lot different structurally, and no other structures between the two are even close to similar. So
Okay, now you're on the right track. What's something major that they have that's very different? Or one has, the other doesn't have at all?
legs. Turtles have, legs and so on.
And a tail.
More underlying.
Whoa.
Bones.
Face.
His name is Bowman.
Bones, right? Considering a turtle is a vertebrate and a snail is not, that's a pretty big distinction right away. That you can't get more underlying than bones, and if one doesn't have bones, the other one does. It's a pretty good chance that they're not related to each other. Right? This isn't an episode of Family Guy. You can't just not have bones. So when you think that it's convergent, you have to have a reason for it. So I would say convergent, but the only reason you know that it has to be convergent is because you know they're not related. One's a vertebrate, the other one's not. One has bones, the other one does not. They don't have any similar underlying structures. Superficially, they are similar. That's why it's analogous. That's why it's convergent. So make sure you can talk about why you know that they're not related. You can't just say that they're not related and not support that. You have to have a reason for it. And I had an answer earlier that was kind of on the right track. They said that one's a reptile, I guess, and then the other one is a mollusk. And that's true. But what's the difference between a reptile and a mollusk?
No one knows.
Reptiles have bones, the other one doesn't.
Bones or no bones is a really big difference right away. So that would be actually something you'd want to talk about.
I just gonna.
So make sure you don't be vague in your answer. Explain why you know that they're not related, why it has to be convergent. If I said turtle shell and a tortoise shell, would it be convergent or divergent?
Divergent.
Probably divergent. And how do you know that?
Because they probably have a common ancestor.
Why would you assume that?
Because
they're
horses
pretty
have to
similar.
get to the land somehow.
Is there underlying structures or
They do have similar underlying structures. In fact, the shell is extremely similar as far as what it's made of and what it looks like for the most part. The difference would be that the turtle usually has the kind of more sleek, slim shell body, so it can swim a little bit better. The tortoise is a lot bigger and it's more mounded, curved, I would think. So they are different traits. They could be homologous traits in that case. And you would assume that they're related because turtles and tortoises are both reptiles. They have the scales. They have the bone structure that's similar. They have a lot of things in common. So make sure you can answer that question appropriately. Coevolution. I don't know if you have a blank to fill in, but we're going to have to do a couple examples for this. Let's focus real quick. You're talking, you're not listening. Coevolution. The easiest example for this is usually an evolutionary arms race. You guys know what an arms race is, right? The U.S. and Russia, Cold War with that thing, but actually it was more about nuclear weapons, right? Cold War and everything else. So evolutionary arms race. It's kind of like an arms race, but in nature terms. So you have an example that would be something like this. You could have a crab and a snake. Now this isn't like the last question. We're not talking about whether these two things are related or not because we don't care. How do these two things interact with each other in their environment?
In the water.
What is one to the other?
Predator.
Yeah, this is a predator. It's going to eat the snake. But we've talked about how evolution works. And those snails may have a range of traits as far as that shell is concerned. It could be a really soft, delicate shell. It could be a really hard, spiny, strong shell. In this scenario with the predator-prey relationship, what do you suppose the evolution is doing to those snails? What's happening to those shells over time? They're getting harder, stronger, right? They're spinier so that it hurts if you would try to bite them or something like that. So it's pushing in this direction because of natural selection, right?
Yeah.
But the crabs have responded to that. How are they evolving? They're getting bigger, stronger claws. So if you would look at a crab from a million years ago, maybe they don't have those big giant claws that we're used to seeing because they didn't need them yet. They've evolved those because they needed to be able to break this snail shell. So as one thing's happening, the other is also happening at the same time. In order for the crab to still be able to eat snails, it's going to have to do some evolution on its own, so it could have a big or a small claw pincer to try and break that shell open. And natural selection for it is also pushing in a certain direction in response to that snail. Right? If there were lots of soft-shelled snails, you wouldn't need a big, strong claw to break it open. But once you do get harder and harder shells, they're going to need bigger, stronger pincers to be able to get into that shell so that they can eat that food. So one's responding to the other. Another example that we've already talked about. 100 years ago, we invented something that's just basically reimagined, retooled modern medicine. What was it? Penicillin.
Allergic to that.
But what is bacteria's response to that?
Gets stronger.
They end up becoming more and more resistant because some of them naturally had a resistance to that drug, and those are the ones that are surviving. So now we have bugs like staph infections that cannot be killed by penicillin anymore. So what's our response? We make a new drug, a new antibiotic that'll kill it, but the same thing's going to happen again. Some of those will naturally have some kind of resistance to that new antibiotic, so we just keep going back and forth, back and forth. That's the evolutionary arms race again. And eventually we might run out of options, and then we're kind of in trouble because we have bigger, badder bugs than we ever used to have. Maybe that's what could cause us to go extinct. Overuse of antibiotics. So that's why I told you guys, try to make sure that you're following your doctor's prescription all the way through. Practices like in ranching where they might give a low dose antibiotics. That's a really bad idea, actually. If you want your herd to be stronger, right, you'd actually want to leave them alone and not breed superbugs. Right? If they actually get sick and a vet prescribes an antibiotic, it's a full dose, great, that's fine. But otherwise, the low dose in their food is a really bad idea. Not a good practice. But it's all because of that evolutionary arms race. Right? One can respond to the other in turn. Now, it doesn't have to be an arms race. Some of the other types of examples that you can come up with are less crazy. One example, we talked about snapdragons, but do you even know what a snapdragon is? It's a flower that, like, you pinch the side that pops open. That's why they call it a snapdragon, because it actually looks like it's a dragon opening its mouth. But the whole purpose of that flower, a bumblebee is just heavy enough that when it lands on the lip of that flower, it opens. But a little fly that lands on it would not be able to open it, so it can't get inside of there. The basic idea there is probably it doesn't want the fly in there because flies tend to lay eggs inside of the flower and probably parasitically kill the flower, so it doesn't want that. but it wants the bees to pollinate. So it's evolved so that just that weight of the bee could open it up. But that can't be a coincidence, right? It doesn't happen by accident. Those two things depend on each other. The bee needs the flower needs the bee. So they have that trait for a reason. The other one that's kind of flower bug related, in tropical regions, there's this, I don't even remember where it was. I read it in one of the books, it's a biology book. But there's a flower that's long and skinny, like cylindrical, that's like a foot long. And there happens to be this moth that lives in the same area that has a tongue that's also that same length, so that it can actually get to the nectar, to the pollen inside of the flower. That cannot be a coincidence. That had to have happened by coevolution. It just wouldn't make sense. That tongue would have to hinder that moth otherwise. It has to like curl it up so that it can actually fly around without getting caught on stuff, right? So just to have those traits in common, it can't be a coincidence. That'd be coevolution. So it's not always predator-prey, or for the superbug, you got the humans versus bacteria. That's a parasite. You always have to have some kind of close relationship, but the relationship doesn't always have to be an arms race type thing. When you're talking about the bugs and the flowers, they're not responding in response to each other as far as killing each other is concerned. So I wouldn't necessarily call it an arms race. So sometimes it's actually an arms race because you have a plant that's poisonous to that bug so that it kills the bug as opposed to letting it just eat it up. But when you're talking like the bumblebee and the snapdragon, or you're talking the moth and the flower, those can't be a coincidence. That has to be coevolution, that those things evolve together to make something happen. So they're in close relationships, and they evolve. Oops, I thought I had the highlighter. They evolve in response to one another, some way, somehow. That close relationship can be a predator-prey relationship. It can be a parasitic one, like the bacteria and us. It can be a mutualistic relationship, like the bumblebee and the flower. They both get something out of it. But if they're in close relationships, often they evolve in response to each other. Okay, and then we flip this switch here. We're going to talk about extinctions for a little bit. Extinctions, again, are kind of important. There's usually a normal background extinction rate, but every once in a while, some abrupt and global event can happen that causes mass extinctions. A mass extinction is only when over half of all the species that exist go extinct all at once, which is a huge number of species. We have millions of species on the planet, and millions that we don't even know about. So things go extinct all the time, and that's normal. But again, these can be important for evolution because it's only because the dinos died out that we could actually evolve. So without that event, we might be in trouble. What event do we think caused the dinosaurs to become extinct?
Asteroid.
Yeah, we do think it's the asteroid one. That one has the most evidence that we can find because
Where's the crater?
of a lot of different things.
Yeah.
They don't know
huge
that.
crater off the Gulf of Mexico.
But there's a huge crater off the Gulf of Mexico that they would assume maybe, and they've tested it, and they think it's about the right time period. They also have studied that layer of soil from that time, and they found a spike in a certain element that really can't be found in that concentration just randomly, so it probably was part of the asteroid that exploded and the debris went all around the
What's
planet.
the other one?
What's that?
What's the other theory? Yeah, what's another theory?
Other theories, maybe like huge volcanic eruptions.
Malaria.
I thought one was an ice age.
Sometimes they think it's like an ice age, but that asteroid, remember, that would actually block out the sun, so it would affect the climate on the planet. It did probably get colder, and because there's no sunlight, there are not very many plants that are doing too hot. And since most dinosaurs eat plants, that's really ultimately what killed the dinosaurs. It's not the impact of the asteroid itself. It's the loss of food and the change in climate and everything else. But anyway,
Mesothelioma.
You need to put a graph in your notes, so draw a little picture here. On one side is the extinction rate, right? Anywhere from up at the top, which would be 100% down to 0, obviously. And this would just be time. Little t is always time. So it's normal for things to go extinct because the earth changes and not everything can cope with it. It's just the way the world works, the way nature works. So there's always going to be a certain level of extinction. But every once in a while, something happens that causes a mass extinction to occur. So mass extinctions only occur when you go above 50%. So normally it's a very low, it'd be just a 1%, maybe less than 1% of the population or of the total species become extinct a year. But every once in a while something happens and then all of a sudden you have a lot of organisms that die out. That would be a mass extinction event. So they've actually graphed this over time. It's a little bit more, it's not quite as smooth as the graph that I'm drawing. It jumps a little bit all over the place. But there have been multiple mass extinction events in the history of our planet. Some of them are smaller than others. Some of them are bigger than others. One of the most drastic mass extinction events happened in really early Earth. Cyanobacteria caused it. You guys like oxygen, right?
Oh yeah, man.
But before oxygen existed in our atmosphere, there were a lot of anaerobic organisms that existed that all went extinct as soon as that oxygen was made. And that was one of the biggest mass extinctions that ever happened. And it was because cyanobacteria started doing photosynthesis, because they started making oxygen. Now, it wouldn't be possible for you to exist without that mass extinction occurring, but it was huge. Now, the reason we look at this is not, well, a lot of it, we can look at the history patterns of what's going on. This is actually how we define our eras and our periods of time. So the end of the Mesozoic is the extinction of the dinosaurs, that mass extinction. The Cenozoic is our current era that we're part of, and it's predominated by mammals because the reptiles kind of lost their grip, their toehold on everything. Right? And before that was the Paleozoic era. So we kind of mark the end of periods and eras with these mass extinctions. But one of the things that we are kind of concerned with is this thing's moving along, right? And we find ourselves probably somewhere around here on an upswing right now, which is kind of scary, right? Since the background extinction rate in the last 100 years or so has started to increase, that could mean something very significant for our near future, right? We are likely headed towards a mass extinction of some kind. How big will it be? What organisms specifically will go extinct? Who knows?
Us.
One of them could be us, though, and that's the problem. And even if it's not us, we might find a completely unrecognizable planet on the other end of this thing. So it might be difficult for us either way. So there's a lot of things that we talked about in biology
future,
due to
you're talking
this.
like another 9 years.
Mass extinctions are natural, they should occur, and they're just going to. That's just the way everything works. But our problem, what we're worried about is we think that we're actually causing this mass extinction to happen a little earlier than it needed to, right? So things like climate change that we're concerned with, global warming.
It's a myth.
You can pretend like it is, but when 99% of scientists agree that it's a real thing, just because 99% of the population are uneducated doesn't mean that their vote counts as far as is
Yeah,
it
but if
real
you
or
look
is it
at
not.
the Earth's geological history, it goes through warm and cold spells, and
It
we're like
does.
at the peak of one. So it'll start going downhill soon. If you look at the history of the Earth, yeah.
Yeah, sometimes
The
it's
problem
it
is-
can be cold for extremely long times.
The problem is it's supposed to change,
Yeah, we're going up right now.
but
So
it's
it'll
not
still get warmer.
changing the way we would predict it to. It's changing faster than we would expect it to. So you can explain it like that if you want, but that doesn't change the fact that something is probably happening. Every scientist who has legitimately gone into trying to discover if global warming exists or not has concluded that yes, it exists. There is a 1% out there, but they don't say that it doesn't exist. They just don't know. They're inconclusive. They're not sure. And then there's a lot of science out there that's really just, like big oil companies trying to put out false information so that you might believe that it's not real, so that they can continue to make money, because that's kind of their goal. But either way, whether it exists or not doesn't really matter. We still seem to be headed towards a mass extinction, so we got to worry about it either way. Doesn't matter what's causing it. What matters is that we understand that it's coming, and we might be able to do something about it.
Do you think that could happen in our lifetime?
I don't know. Nobody really knows. But
Could
considering
happen
we're on an upswing, and sometimes those are false alarms. Sometimes it'll go back down, but if we don't worry about it at least a little bit, and if we are causing the problem, then we should do something about it. That's the point. It doesn't matter what you think is true. If it is possible that we are causing it by doing the things we do, burning fossil fuels constantly, uncontrollably, then maybe we should do something about that. One of the main reasons why we should do something about fossil fuels is because we're running out. We can't use them forever. So it's idiotic to not try to come up with different sources of energy in the long run. Because we know we're going to run out. We have to.
So then why do all these people in the sandhills not like wind energy?
I'm not saying that people don't have opinions. I'm just saying that it's a really good idea to look for other alternatives. And it doesn't have to be
Attention
wind.
students, the track meet tomorrow at Baird
Solar would
has
be
been
awesome.
canceled, so there is no track meet tomorrow.
You could actually make a solar panel the size of like Texas in the Gobi Desert, and it would produce enough energy to supply power for the entire planet, as is right now.
Cost.
It would cost a
Yeah,
lot.
that'd be tons of money.
It costs more.
Plus, it would also take some pretty rare earth metals that we'd probably have to harvest from space somehow.
Yeah,
If
'cause
we're
we
gonna
don't have
make
all
it.
that.
But I'm just saying, there
If we're
are
gonna make
means. We want to come up with other ideas. Okay, so other things, the last couple of things we need to talk about, punctuated equilibrium. So you need to know what punctuated equilibrium is, so you probably have to write something here. Basically, long periods of little change followed by abrupt change. Which actually should sound like something we talked about before. It actually kind of sounds like catastrophism, which we discounted as the way that the Earth changes in general. But there is some notion to some of those catastrophes as far as they can actually affect life greatly. They may not change the surface of the Earth as drastically as they once thought, but they do actually affect organisms on this planet drastically. So you have these long periods of little to no change followed by abrupt change, which looks kind of like this. Little to no change, lots of change, right? Little to no change, lots of change. So we have that punctuated equilibrium. And then we have adaptive radiation. During this abrupt change, and immediately following that abrupt change, usually there's adaptive radiation. Once all the dinosaurs died out, they left behind resources, niches, right, habitat for mammals to take over. So once those dinos died, then we have these mammals that took over all of those resources. And adaptive radiation is talking about how there were actually a relatively small amount of mammals at the time, and now they have evolved into many, many different species that are around today. Right? Adaptive radiation is just saying you're starting from one and going to many, many different species in a short period of time. And that actually happened with mammals in a fairly short period of time. Right at the beginning of the Cenozoic era, they just exploded as far as evolution is concerned. Lots of new species came up really, really quickly because they had those opportunities. But if the dinosaurs hadn't died first, they wouldn't have had those opportunities to radiate. So that adaptive radiation, you're going from one to many. You might want that too, just in case, so don't put it away quite yet. That's basically what the adaptive radiation means. Yeah?
I have a question.
Need something?
So were there mammals on the Earth, like at the same time as the dinosaurs?
Yes.
Yeah. So how come the mammals didn't die?
Yeah, how come they didn't die?